Hello, everyone, and welcome to Handmade Hero, the show where we code a complete game live on stream. We are right in the middle of doing some light probe coding on the CPU side. Um, we're being a little conservative with this game. We're not trying to do GPU side lighting, primarily because we would like to maybe run on lower end systems eventually than that would necessarily imply. So I'm not necessarily sure we want to go quite that route. So we're trying to do something a little bit simpler than we might do if we were assuming that you're gonna everybody who plays Handmade Hero had to have an RTX card plugged in or something like this. But we are right in the middle of that code, trying to update our system to use light probing instead of surface, like actual surface level probing, because that was just too inefficient and also didn't really provide us what we needed for sampling like things that don't contribute to lighting, so sprites and stuff like that, like on the ground or like ground cover, grasses, and things like that we want to be able to sample lighting from. It was a little bit confusing how we actually wanted to do that. We could have done it, but it was going to be a little bit weird, right? It couldn't have been very dynamic, and we would have had to have sort of extra procedures in place for handling sort of special edge cases and all that sort of stuff. So we're just trying light probes as a way of sort of cleaning that stuff up, having a uniform sampling regime for everything, and giving us a way to undersample our lighting as necessary, because again, we don't want to end up with a lighting system that's so expensive that we can't run a really crappy version of it on low-end machines and still have something resembling the look of the game, and then crank it up to higher levels on higher machines or something like that. We want some flexibility there, and we didn't really have it before. So that's mostly what we're looking for here, solving those two problems. I'm going to go ahead and get started. And if you remember where we were at, we just finished adapting the raycaster to return the information necessary for us to do light probe sampling during light propagation. The reason we're doing that is because the light probes are what store the information now. They are what will store the information. Surfaces themselves will not store that information. And since surfaces won't store the information for lighting, it means that we need to be able to get from a particular surface hit back to a lighting answer, and that requires querying the light probes with a point and a normal. So that's what we actually needed to get. That means that our hit result, so if we go down there and look at our raycast function, excuse me, our hit wants to have slightly different things, and so that's what we did. We changed to returning a hit normal, which we got pretty efficiently. I was pleased. There's probably slightly more efficient ways than what we're doing, but we did a pretty good job of that yesterday. I was happy with what we came up with. It's not the stupidest thing in the world. And this hit position, which is trivial to get, obviously, whenever you do a ray intersection, you know the t value, so all we had to do was just march forward by the t value and you get the hit position, so that's pretty straightforward as well. Now, there may be easier ways to record that. I'm not exactly sure if we're doing it quite as efficiently as we could in here. It's possible that we already have the information necessary to directly reconstruct the hit P, and we could do other things like that. Excuse me. Yeah. So, we'll see. But generally speaking, we're in good shape. We return all the information necessary, so the reference color, the reflectance color of the surface, the point that you hit, and the normal at that point. That gives us the ability to propagate that information along the ray to whoever was trying to sample it, which brings us to the part of the code we want to work on today, which is where we actually do that propagation. Now you can see how this particular function works, and we're going to rework it a little bit. This was designed to do light probing in a very specific way from surface to surface. So it would cast rays from surfaces to hit other surfaces and convect the light along those rays. That's effectively all we were doing, because that's all we wanted to do. And remember, this solution is a temporal solution. It goes over time. So we didn't consider multiple bounces in a single propagation step. And the reason for that is because every frame is basically a new bounce set, right? So we're counting on multiple frames to do our multiple bounces, and again, that's for efficiency. Obviously, we could have done multiple bounces in a single frame, but that just doesn't make sense from a performance standpoint, because you're never going to be able to take enough secondary rays to really make enough of a difference there with the kind of performance profile that we're looking at. So what we want to do is let that temporal sort of crank do the secondary bounce propagation for us, and that of course gets us an arbitrary number of bounces as well, because every frame is a new bounce propagation, and since you can propagate off all after each frame you're propagating light off of a new set of bounces, it means that you're effectively getting 4, 5, 6, 7, 8 bounces down to the diminishing point for sure, because of depending on how fast you blend them in, obviously you'll get different levels of contribution for those secondary, tertiary, and quaternary bounces. But generally speaking, even if you're assuming a very reflective paint of some kind, 80%, 90% light transmission, you still only need, 5, 6 bounces or something before you're kind of getting to a point of diminishing returns. So you definitely need secondary, tertiary bounces for sure. In any realistic scenario, those are going to contribute actually pretty important information to your lighting, no question. But at some point, 9, 10, 11 bounces, you're probably done at that point with anything that's really going to be that perceptible as anything other than a general light boost, maybe a little bit of a general light floor boost. And so that's something we can easily account for by just turning our lights up a little bit, right? So it's the character of the lighting that you're trying to capture. After a couple bounces, you've kind of got the directional stuff under control. And when you get out to, bounces above 8, let's say, you're kind of in a position where you're really just talking about adding an amount of light to the scene and not really having to care where it's coming from. And so at that point, you can compensate typically because it's just, again, the more bounces you're talking about in a diffuse, because remember, the difference between a specular and a diffuse bounce is that a diffuse bounce of lighting spreads the light out, right? It's going fairly evenly throughout the scene off of the point that you hit. And that's the only kind of light transmission we're really simulating here. Specular bounces, which are those sort of bright highlight bounces, they're almost reflections, right? The more specular something is, the closer it is to a mirror, effectively. Those kinds of transmission, they require, if you have a lot of those surfaces, that's where you start to require more bounces. Of course, those are also more easy to simulate with ray tracing because you have less rays, because every time you hit a surface, you only have to cast out a narrow band of rays to find your answer. This is also why, like, modern ray tracing in hybrid approaches, like in games where you use hybrid ray tracing in sort of the modern RTX optimized kind of way with stuff like that, that's what they are using that for, right? They use the RTX to handle the glossy reflections because those are easier to ray trace, right? The wide diffuse distribution, you typically need something more like this. So that's the part we're trying to tackle here. And it's also the part that's most important for our game because we want a soft kind of warm look to the game. We don't want a lot of specular. That's not much how the art looks. It's supposed to be kind of a warm, diffusely lit kind of a game anyway. And so again, we're trying to design a lighting solution that simulates the kind of lighting that we want, and specular isn't really part of that equation for us. So, spot specular is something that we might want to put in. That's fine. That's a render time thing. For light propagation, we care about the diffuse part. And so that's what we're working on here. Okay, so what we want to do is fundamentally change this loop a little bit. We were talking about going from sample points, which were all on surfaces before, and we were going to collect lighting from other sample points on surfaces. So it was from a point on a surface, we'd cast, we'd see which surface we'd hit, we'd look at the sample points on that surface and get the light back from it. That's not what we're doing anymore. What we want to do now is similar. Instead of looping over sample points, we're going to loop over light probes, but you can consider those to be the same basic thing, right? If we just call a sample point a light probe, we just change the name, then this part is the same. So conceptually, this part is changing only the very smallest amount. It's really a naming difference to that effect. And the reason we did that, again, is because we don't want these sample points to have to be on surfaces. So the reason we're calling them lighting probes, and the only real conceptual difference there, is that now these sample points are floating out in the world. They're not embedded in objects. So that's the only conceptual change there at all. Otherwise, exactly the same. We're going to loop over them and we're going to cast rays out of them. So exactly the same otherwise. However, the next part is the part that really changes more dramatically. When we do our ray casting, we're going to get out a point and a normal in the world. That point and the normal in the world, and a reflection color as well, is the surface we ended up hitting. And here's the big change. What we used to do is for each one of those hits, we would look and say which of these surface points are around there, gather those surface points up, average their lighting together based on how close they were. That's our lighting sample. We're not going to do that anymore, because now what we're going to do is go from that point that we hit, and instead of gathering surface points on that same surface, we're instead going to go look up what light probes are nearby and average the light probe lighting together, right? So that's the primary change we're really going to be making in this loop here, is saying let's switch from a system that's gathering surface points on a surface for our lighting to gathering lighting probes that are floating in the world and averaging them together in sort of a trilinear blend. So that's a fairly big difference, but again, conceptually, it's not a huge leap, because we're doing almost the same basic operation. We're doing a spatial gather followed by an averaging, weighted blend, really, right? And so it's the same basic idea, it's just a very different type of gather and blend. That's really what's going on here, right? And so now we just need to go do that. It's just plugging away to actually do exactly what I just said, but there's no mystery to what's going on. It's exactly that. So let's step through this loop step by step, take the if zeros out, get it compiling, and that's pretty much all we really want to accomplish today. Again, lighting is slow. It's a lot of work. A lot of math has to be optimized. So it's the kind of thing that's not a fast thing to do typically if you're writing it by hand like this. Okay, so we know we're going to take a look at the lighting solution that we get, and we know that this compute light propagation call, as you see here, this compute light propagation call really wants to be multi-threaded. This is a situation where we really want to use all of the resources of our CPU, because if we have 8 cores, 16 cores, or one of these crazy new AMD chips with 64 cores of logical CPU on there, or is it 128? I can't remember whether they have 64 actual cores or 32 actual cores with hyper-threading. I don't know. Who knows how many logic cores there are, but let's point there's a lot. And so if you had some crazy machine with tons of cores, which are becoming more and more common these days, and AMD is pushing them more and more, we want to use them all because we can just crank up our lighting quality. Our lighting quality will just get better and better and better the more cores you give us. That sounds great to me, right? So what we want to do here is just go, all right, compute light propagation. Let's grab that solution out that comes from the lighting work packet we've been given. And again, we expect this compute light propagation. We want to make sure that it can be called from many threads at the same time with just different chunks to work on. And so that's something we want to keep in mind. We don't want to do anything in here that we think would lock up our system on doing some kind of a query or something that would be a problem. And so off we go. So here we are. We're going to do our random series here that we've got. That's going to allow us to pick random rays that we sample out of or other things like that. So we kind of want to do a thing here where we do a sampling. You can see us getting a sample point entropy out that's just a single value we're going to use. I think for, well, let me actually see what that's used for. Are we actually still using that? Yes, we are. Okay, so you can see what that's doing there. The sample point entropy is basically randomizing in our, so if you remember how we do the our sort of casting throughout the world, our sample point entropy is given to us as a, trying to think how to explain this. We don't want to have to generate ray directions every frame for every point, because if we did, that generation of the actual random points would actually dominate our runtime. We can probably raycast about as fast as we could generate those points, so it would be a really expensive thing to do. So what we already did in previous episodes, if you saw them, is we created a sort of set of points we can use for sampling. That's like a little hemisphere we can use to cast out from. And what our sample point entropy does is it just says, look, let's pick random sets of those that we're going to throw out from our individual sample points, right? So if we're doing a block of sample points, we want to make sure that each frame, we pick a different random sample direction from our set of sample directions. We don't want to just always sample the same direction because that'll lead to pretty bad artifacts. We want to get some noise in there so that we can sample a broader, sort of a better coverage of the things out from it. So that's what we're doing here, and we want to keep doing something roughly like that. So that part of the code probably wants to stay the same. The only real difference we probably want to make here is since our light probes are points floating in space now, we probably don't want them to do hemispherical sampling. We probably want them to do spherical sampling. There's a couple other things we probably want to do, such as remember which direction, roughly speaking, which directional color each ray is designed to contribute to, so that way we don't have to figure that out either. And we'll see that as we kind of go a little bit further on in the process. Now, moon color is something that we want to sort of make a little bit more procedural. I'll put a to-do in here for that just so we remember. We generally speaking don't want to add a sort of ambient moonlight to things that don't actually get lit by the moon. And so, for example, when you go indoors or if you are in a dungeon area, you know, we wouldn't expect moonlight to really be getting in there. Or if it was getting in there, it should go through an aperture. So we want some way of controlling that potentially. However, we may also just want to put in like ground patches or something that would prevent you from getting to the moonlight. I don't know. But the reason that this is important to understand is you might say, well, wouldn't you always hit something if you're underground? Wouldn't you always hit like the ground when you cast up? The answer is yes, you would if you actually could reach it. But remember, when we simulate, we only simulate a local region. We don't want to bring in the entire world for raycasting. It'd be way too expensive. So we may need to have some idea of like a basic ground plane that you can't get out of, so that even when everything's been paged out, you will not get moonlight going into your dungeons simply because the actual ground was so far above you when you're like 7, 8 dungeons deep, right? You don't want to have to load up all of the ground tiles to just so you hit them and don't get moonlight. That's really inefficient. So we probably need some way of controlling that moonlight in a way that's not going to require us to actually compute the fact that there was a ground up there stopping us. So, you know, something to just be aware that that's got to work out, right? Okay. So, and we could do a really simple cheat for this even, right? Like, you can imagine cheating this really easily when we actually go to put our light probe in there. So you look at this is our light probe structure. We can pretty easily extend this structure with a simple flags field. The flags field could say things like whether there should be an ambient light and which ambient light it is, stuff like that. So we could hack this too. When we place those light probes, we know whether we're placing them in an interior or an exterior scene. So we could cheat that, right? That's a thing that's easy for us to cheat out. And so we've got a lot of options for dealing with this. It's just we need to deal with it some way at some point. So let's go in here. When we start looping over sample points, what we really want to do here is change the nomenclature just to understand what we're doing, but otherwise it's going to stay the same. We're not going to be looping over sample points per se. We're going to be looping over light probes. There's a difference between those two things, obviously. And we want an understanding of what's going on there. So we want to actually change this to a light probe index because that's what we're actually doing. But otherwise, we want it to be the same. We're probably going to want to have us loop over the specific light probes that we're doing. So this should be like first light probe index. And that should be coming from our work function here. So first light probe index is going to come from our work order. And one pass last light probe index, same thing, right? So we just want to change our nomenclature so that we understand we're looping over light probes, not sample points anymore. They are our sample points, but we just want to change that naming so that people understand when they're looking at this code or when I'm reading this code later when I've forgotten how it works. It's clear you're looping over the light probes. Those are our sample points. Off we go. So now lighting point, which is this thing here, is not going to be used anymore. And in fact, this stuff is all going to go away. We're going to want to delete this, and this thing here is going to get, right? And so when we send down our light data, we're going to be sending down a very different kind of light data, more like what we experimented with at the beginning. We're going to be sending down more of a voxelized piece of lighting information. And so, just keep that in mind. All right. So here's our lighting point. We want to change this now to be light probe. It's going to be straightforward translation. And so we're just going to grab that out in order in the range that we're given. And again, that range, just in case you're forgetting, that range is effectively the slice that this particular core in this particular round is going to operate on. So we've sliced up our set of light probes and we're handing them out to different cores effectively, right? So each core will operate on a different set of lights. All right. So the first thing I would like to do here is we probably actually want a little bit of a nasty if statement here, I'm guessing. Now maybe we don't, maybe we do, but we probably want to take our light probes here and have some way, well, no, actually, you know what? We would do this at the head end. So no, this is fine. We're going to keep doing it this way. So we probably want here to say, all right, what are our light probes? Let's go ahead and grab those out of this range. And then when we come in here, we're going to want to take the way that we were generating our rate casting before, excuse me, and we're going to want to modify it a little bit to do what we're doing. And now you can see here, actually, this wasn't really something that we talked about before, but if you look at what's about to happen here, we're going to be able to simplify this code as well, which is really kind of great. So if you look at what had to happen before, our lights were on surfaces. That meant that we only wanted to sample hemispheres around those points. Because we were only sampling hemispheres, it meant we needed a basis system, like a three-dimensional structure around those lighting points so that we knew how to construct our hemisphere. And that meant that every time we took a sample point, we then had to do work where we would do a bunch of FMADs here. Well, actually, more like a bunch of, well, they are FMADs. A bunch of FMADs. We would have to do those to recreate what the hemisphere looked like when placed into that sort of hemispherical context for the surface we're on. So if you just, again, to bring everyone up to speed, because I know some people, you don't have a chance to watch everything we do here on Handmade Hero. Remember, we're creating a hemisphere of directions that we're going to use to sample. That hemisphere is stored as a static set that we use for our sampling. We can't do a hemisphere just arbitrarily, because if we have a sample point with a direction, it's on a surface, we don't want to cast back into the surface because they're all just going to hit that surface and not give us any information. So we needed to orient our hemisphere so that it's pointing away from the surface, right? We don't need to do that anymore. We can sample full spheres of lighting now because we're using points floating in space. Another reason why light probes are a good idea, right? And I already explained why I didn't use them at first. Is because I had a thing that I didn't think I could do in my head, but it actually turns out you can do it. That was just a gap in knowledge there. So the light probes can handle that for us, which means that this stuff actually will go away, right? We don't actually need that anymore. We can say, look, let's get rid of that. Let's load up the sample point for our light probe, and let's load it 4 times. So we're just basically doing a load and distribute here. It's called a broadcast sometimes, I think. But we're basically going to load that up, and we're going to load effectively SIMD registers filled with the X, Y, and Z, one SIMD register each for the X, Y, and Z of the light probe's position, because that's where all the rays are going to come out of, right? Now, remember, we've got some debugging stuff in here. I don't know why this doesn't say if Handmade internal around it. It should, because it's debug stuff. But, whatever. We want to leave that in there because we're going to have to debug this, and we might want to lean on some of this stuff. So I'm going to make sure that this still works. Again, here's that light probe point, so let's just put that in there. And this was showing us the coordinate system of this thing. We don't have that coordinate system anymore, so I'm just going to go ahead and throw in a generic coordinate system, because that's what we'd actually be using now, because we don't change per point. But again, just leaving this so that it's still the same. There we go. And so now when we come in here and we want to take our sample direction, you can see us doing that here. This part here where we recreate the sample direction by reinterpreting it in the coordinate system of that sample point, that's the part we don't need to do anymore, right? So we can just delete that whole thing. This is the sample direction right here. We're good to go. It's the ray direction effectively. I don't know why it's called sample d4x. We could just call this ray direction. That seems a little cleaner to me. And off we go. And again, I don't think we need to do really anything else here. These sample points are just good to go with the sample pattern the way it is. Off we go. And we just make sure our sample pattern is nice and big. I think we would be fine. I think. I mean, don't quote me on this, right? So anyway, you can see the entropy baked in here. We're doing this sort of stuff so we don't have to do cosines and sines at runtime. I think this just creates a bunch of different like randomized spheres that we can use. We'll deal with that stuff later. Not important right now. But point being, we're just going to assume that this sample points here will get us a full sphere worth of samples when we go and modify it. So they would just trust that this needs to be a whole sphere. I'll put it to do in here. Okay, so we know we need to do that, and that's fine. It won't be hard, I don't think, to modify our hemisphere point sampler generation system to just do a sphere instead of a hemisphere. The reason for that is I'm pretty sure that the way we did the hemisphere was just doing a sphere and chopping it off, right? So I think all we have to do is to remove some code probably from our hemisphere sampler, where we were just previously saying, hey, let's limit this to just the hemisphere. But I don't know. We'll go check it out. It shouldn't be hard anyway. All right, so here's our raycasting call. We have that here where we call our raycast, and that's just a little walk. This will probably, I would assume, when we do an optimized build, this will get welded in. So it would probably just get inserted here because it's the only place it's called. And that's the way we want it. We want it to just be merged in here because we want it all to be nice, one simple loop, no function call overhead, and so on. So you can see here we're creating the ray P4X structure, but we don't need that because actually this has that in it. That's just going to be the ray.p, right? So this right here is this. So it's already been computed by the interior code. That goes away. And so then we're just left with the part where we need to actually compute our sort of the actual light gather that happens. So we're going to loop over the number of rays we were asked to raycast, and we're going to raycast them. In here, we're going to want this to be a handmade internal. I think we want to, again, leave that in there. This has to be light probe index. And this right here should probably be debug probe index that we should change. But again, probably want to leave that in there because we will have to debug this code. And we want all the help we can get when that comes to it. So there we go. And in here where we've got this part where we're pushing the debug lines on here, looking at what's happening here, again, sample D4X, we still have, that's just our ray direction. That all looks fine to me. This part here, I think, is a little bit different. Let me just see what we have left. So we have the hit point. So I think all we really want to do, instead of doing endpoint, instead of doing this, all we really want to do here is probably do a check to see if the thing was a hit or not. So we probably want to just do if hit, do one thing, if not, do another thing. We don't have a T-ray anymore. So in this, what we'd like to do is say, all right, if we hit, draw the hit. And the way we would draw that hit is just by saying, okay, we know that we're starting from the ray origin, like so, right? Which is light probe P because we don't want the full 4x version of it. So we're starting at light probe P, and then we want to end at this position, right? So we want to end at what the lighting system tells us. So we need to be able to extract that. In fact, you know what? Here, We only need to call this once, and we only need to do that. We'll just build endpoint differently in the two cases, right? So what we'll do is we'll say, okay, we've got the endpoint here. We can just say that we'll move a certain amount along it, like that. If it didn't hit, oops, like so. So that's all we need to do there. I think this is also all we need for endpoint then, right? That get component calls exactly what we want. It unpacks a SIMD version into one slice, so it takes one slice of it out slowly. So what we want to do there is the exact same thing. We want to take the hit position, so the hit position, which is this, and just unpack that into the endpoint, right? And so there is all we really needed for that. I could also make this be a little bit squinkier, right? It could be this if we wanted it to be. Not really a big deal. Right? Something like this. So we can do something like that. I don't know if that's good or bad. Doesn't really matter. It's just some debug code. No one cares about it. And so that gives us everything we really need there. And yeah. Right? Seems good. Off we go. So that gives us the ability to draw one of these things. And again, like I said, think we're going to need it because we're just going to run it. It's not going to work. We're not going to know why, right? We're going to have to debug it step by step. Make sure our array generation is correct. Make sure our array casting works properly. Make sure, right? All right. Excuse me. So now we get down to the actual transfer. This is the actual expensive part. The two expensive things are the cast, which you saw, which is actually quite fast per primitive, but it has to do things like traverse a little bounding hierarchy and stuff, and that sort of thing is slow. There's just a lot of tests, that go on and things like this, so it's all good. So you want to go ahead and do that, and the other thing we want to do, excuse me, we want to go ahead and do that. We need to be aware of that, right? That's one slow part. The other slow part is here, and so that's the part we have to work on now. And that's once we know a particular hit point, we need to actually get the lighting sampling. So I think we probably want to try to do this wide for as much as we can. But again, because the SSE instruction set is really not very good, it doesn't handle fetch. And so the thing that you always have to end up doing is as soon as you want to sample a texture or a spatial gather or whatever, you have to downshift into scalar. It really sucks, but that's just the way it goes. And that's exactly what we're going to have to do here. Now, we can still try to write this as fast as possible, and we're going to want to do that later because I think it will be an expensive part of the routine. But for right now, what I'm going to do is I'm just going to completely downshift. So the first pass through, there's not going to be any at all. There's not going to be any SIMD in this entire path. We're just going to downsample immediately, downshift immediately to scalar and do everything in scalar. Again, not what we actually want because I think we can still get some SIMD out of this. But for starters, when we're debugging it, let's keep things simple. So the way we're going to do this here is we're going to do the downshift we did here, effectively. The ray P that we get back, that ray position, that ray hit position, that's going to give us the point where we want to sample our probe. We also have the probe sample normal. I'll get that back for now, like so. And so we get those two things. I don't know why this is normal instead of N. Just because, I guess. There we go. So when we get back the P and the N, that gives us what we need to sample. And again, we have to downshift here because we've got to downshift to do the gather. So what I'm going to do is do the full downshift. Inside the light system here, I think we have like way of sampling that in here somewhere. I don't know where. So here's that code. So this is effectively what we're looking for, right? Get probe lighting for, and get light from probe. You know what I'm saying? So I think if we combine those two, although we may already have those guys. Yeah, we actually have the entire thing. We already wrote the entire thing here. Wait, why doesn't that have a normal in it, though? What? Get probe lighting for is supposed to take a normal. So this is wrong. This was supposed to take a normal and isn't, right? I think we've got a buggy bit of code here, just in terms of what's being passed down. Bear with me for 1 second, because I think we should fix it. So in here, you can see us calling get probe lighting for. That assembles a lighting probe based on the cell position in the UVW. You can see that happening here, and returns you a single probe you can use for your lighting. So in here, when you do this, that's correct, right? Get light from probe. So maybe we just never call that. So maybe it's not buggy. It's just no one ever calls it. I guess no one ever calls it. All right, never mind. So we just need 2 of these to do our sampling. And so let's go ahead and do that, I guess. So in here, where we're going to do our sampling, what we want to do is first say, please give us the sort of composite light probe that we're going to need to do this operation. So that's this call here, right? Where we'd say, give us back for this lighting solution and this spatial index. The light probe spatial index is something that we're just expected to have here. So I assume that's something that we need to get. Well, actually, that's actually something we can just get out of the solution, I think. It's this thing, right? So we get that spatial index. That's the thing we need to use to do our querying, so we pass that along. And then we know what this is here. It's the probe sample P. So that's what we want to build our like composite probe out of. So that's taking 8 probes and smushing them down to 1 probe that we can use to sample the lighting based on like a trilinear filter of the 8 surrounding probes from our current location. So then what we need to do here is we need to actually do the lighting. So we need to find out what the lighting is. That's just a question of saying, hey, for this composite probe and this normal, what's the light, right? And that's it. So once we have that lighting sample, we're ready to do something with it. And the something that we want to be able to do with it, obviously in this case, is figure out how much light our receptor probe, because remember there's 2 light probes involved here. I mean, technically there's 9. There's a light probe we're sampling, and that's not contributing anything necessarily. I mean, it might if it happens to end up being one of the gathered ones. And then when we actually cast out and we get a hit, we gather the 8 surrounding ones in the voxel, smush them together to form 1 composite probe based on our position in that voxel. And then we want to figure out how much light is going to get sent back, basically, to our receptor probe based on this, right? All right. So that's it. That's all we're doing. So when we do that sample here, excuse me, that lighting function is probably garbage right now, and we probably want to go in there and make it better than it is. But we're going to trust that it's written properly so we can improve it later. But whatever it is, something happens here and we get back the lighting amount. That means that this is the amount of light that we expect to get along for that sample normal. That's how much we expect. So, we kind of want this to take more, I think. So this get light from probe. I think what we actually want here is not... It's just not phrased properly. I think what we want to do is get light from probe. This should not be N. This should be like in direction or something, right? Meaning, when we get the light from the probe, we want to know what light would be coming from a particular direction, probably. I would think. Although really not. We kind of just want to ask how much light is going out in a particular direction. So I think really what this wants to say is just like how much light goes out in that direction, generally. And the bounce is just going to be colored by the surface normal. So I think it may actually be like this. I think that's maybe the best way to say it. So we're going to query it for like an emission direction for now. And we may need to change up how this works because once we decide exactly how we want to store these things, we're storing them kind of in a basic way now. We might try to store them in other ways in the future. So if we're just a basic idea here is we're going to say in an emission direction. So in terms of the probe sample normal, now that I think about it, it's unclear to me that we actually need that all that much. I'm wondering if maybe that was just a waste of time to actually compute those normals to begin with. Like maybe we don't even really need them. We could just say that, look, we're just going to sample how much light would come back in the direction we're trying to find, right? So I don't know. And, in terms of the probe, yeah, like I just can't, I don't know that we ever actually need that probe normal. Maybe for filtering purposes, but I mean, really all we would need to do with it is say how much light was transmitted in this direction. But yeah. So I think what we actually want here is simpler. So I think all we're really going to say is, look, the direction we want to sample in, the emission direction, right? And when we look at this here, you can see us, when we take this emission direction, I think this doesn't have to be normalized. It doesn't look like it has to be normalized because we kind of do a normalization of it here. So I think the emission direction is fine. It can just be arbitrary. I don't know, but I think that's okay. It plays a little bit because this is not a 2 norm, it's a 1 norm. We talked about that before. There may be reasons why you need to normalize to the 2 norm first. I'm not sure. We'd have to think about that. So I don't know. But anyway, the emission direction here, we pretty much know that it's just whatever the probe sample point is. So basically like where we actually are hitting. We just want the probe sample point and we need to know where we started from, right? So the light probe P, the light probe P is what we're trying to send light back to, and the probe sample P is where we are. So the emission direction we're curious about is that, right? So that's the emission direction we want to get back, and we're going to get back a color. Now, we also need to know, at this point, we kind of want some idea of, like, how much transmission there should be. So we kind of want a cosine fall off on that thing because a surface that's very oblique to us would not be something that would send much light back, whereas if it's straight bouncing, it would. So we maybe want a cosine term in here. If that was the case, this goes away, and maybe I'll just get rid of it preemptively, and we'll just say this is what we'll do. So this right here, we actually want to do a normalizer 0 on to make sure that this thing is normal, right? And so when we do this emission direction, this really wants to guard for div by 0 probably. Which will probably be easier to do in the SIMD version anyway. When we do the emission direction here, and we're ready to go, we now need to take into account that probe normal, and here's the only place where I think that can really be necessary. So what we want to do here is do the like fall off, like the reflectivity fall off basically, where we're going to say take the inner product of that probe sample n and the emission direction, right? So we're basically saying what we hit, the normal of that surface versus the direction we're trying to send light back. If those are right in line with each other, we send the maximum amount of light back. If they're 90 degrees apart or more, we send no light back, right? That's basically what we're doing. Right, so we basically say clamp that 0 to 1, can't have negative transmission. So if you're behind the surface, how you ever would have gotten behind the surface, I don't know, because this is a raycast, so really that should never happen. But in SIMD, when we SIMD this, it's pretty free to clamp to 0, so we probably just should to avoid any weird edge cases. Anyway, once we get the reflective fall off back, then what we can do is take the actual light sample value. So here's where we do our light sampling. That light sample is just going to be multiplied by the reflective fall off, right? And also by the Hadamard product of the reflective color. So the particular thing we hit, remember in that ray, I have to get the ref color here. Whatever we hit, that can have its own color. So that allows us to have like walls that themselves change the reflected light so that if like a wall is entirely red, it will reflect red light instead of reflecting white light when white light is shown off it and so on. So we want to support that because we're going to probably want to use that later, even though we don't really use it right now. So in here where we do reflective fall off, we do the Hadamard product of that light sample there. What we want to do is add that ref color in, right? And so that gives us the actual like light transmit value. That is how much light we should be sending back along that ray to the light probe, and it also contains what the RGB color of it was. This stuff where we get light boxes and this garbage here, none of this is relevant at all anymore. This all goes away. It's not getting as simple as it looks because remember, all this crap has to happen now. So it's actually still very complicated. It's just hidden inside these two routines, which is where we'll have to start bringing more optimization to bear in the future because, you know, that's not really going to be sufficient. So anyway, that's all we really need to do there, and that is what will give us the final value we're actually going to use for our transfer value. And you can see here, it looks like we already got that. It's called transfer PPS. So I think actually we just do that. And then the rest of the routine would work correctly. Looks like here actually the angular fall off was already coming in here sort of. So, all right, so I guess this stuff just wants to be done regardless. So it looks like this code just wants to be done for everything. I guess you can't do these though. Well, wait, but you can't really do that for everything because you don't know the normal. And yeah, I don't understand. All right, never mind. I was confused there. This can only happen in here because you don't have a hit point otherwise, right? So I'm not sure what any of this was doing there. This, yeah, this is just garbage. This doesn't look right at all. So I'm just gonna delete it. All of this looks wrong to me. So yeah. The accumulated weight, I don't know what that would be for now because we have pretty much a consistent. We don't need that anymore because the accumulation could just be done matter of fact. Like the light probes can just be, you can just sum it in here. You don't need a secondary pass at all. Because you know what the weight, you know that the weight is just however many rays we cast per probe, period, right? That's what happens. So I don't think we need this anymore either. I think we can just do a pre-multiply by whatever that weight is and be done. The accumulated weight isn't a thing anymore. So I think all we really need is the accumulated PPS. That can just add the transfer PPS back in there. Photons per second, I think is what we were sort of calling that. And the direction is just not a thing anymore, right? So I think that's all we really need to do. Now, we need an additional piece of information here because when we do the accumulated PPS for a particular sample point, because we're now doing this as light probes, we need to actually remember several different values, right? So we need to, like, when we sort of pack that stuff up, we have 6 color values here, right? So, like, if you look where we do our light probes, each one of them stores 6 light directions, 6 light colors, one for each face of a cube centered around the point. So we want to have a way of summing that, right? And we're only summing into one of those each time. We would probably like to ensure that we always sum one sample into all 6. I would assume. I can't think of a reason really not to. And so this system here, right, where it's doing ray count 16, I think what we kind of want to do is make that be a multiple of like 4, right? So we'd probably want to do like the ray count is 12 each time, and it does 2 samples into each of the 6. You know what I'm saying to you? And so I think what we'd want to do is roughly like this. Right? Now we don't actually want to do a mod 6 here, right? We want to actually just do an easier way of doing a mod round on this guy, because, yeah, like you don't want to actually have to do a mod 6. Although I guess you could kind of work out a way to do that more simply. So what you really want to do, I guess, is when we're doing these samples here, I think we want the sample points array to be able to pull out the directions, right? So we want probably this. You know what I'm saying to you? So effectively in here, when we pull this thing out, we could say that the sample point direction index comes from this. Hopefully that makes some sense. I guess technically, since this is the sample region, I guess now I think about it, that's not actually correct. It's actually the ray index that's the thing that you use twice, so like that. And the ray index just tells us for a given sample which one it comes from, right? Something like this. And there'd be 12 of these, or 24, right? It depends on how many you want to do. Or 18, I guess. 18 would probably be the number closer to what we were doing, right? So I think we want something like that. So we would effectively say, like, okay, we do 18 of these. And then the thing rolls around as we go, if necessary. But I think that's all we really want. And this can be beefed up by the number, right? So the sample point dir index there, yeah, because that ray index doesn't get modded. So basically this thing just has to be the array count of the work sample point dir index, right? So I think that's all we really wanted there. And that way we know that this always gets summed in and they get summed in a predictable way. That way we don't have to track weights anymore, because I don't really think we want to do that. We'll just make sure we always take one sample in each direction every time. Seems okay. If it turns out in the future we really want to be able to take more samples like laterally, because the game spreads laterally more or something, then we would need to change that up. But otherwise, I think it'd be fine. There we go. So what we would then say here is like, when we look at the ray count, we would have a weighting here, like a ray weight. And so since we would know in the case of 18, right? So if the ray count's 18, we know that 6 is the number of directions, right? So we know that if we're taking 6 directions, we need to divide the ray count by 6 to figure out what the weight should be of each one of those, right? So once we know what that ray weight should be, actually I guess it's the other way around. So for example, if we take 6 samples, each one should get a rate of 1. If we take 12 samples, each one should get a rate of 0.5, right? So I think that's what we want to do there. And then when we sum up the transfer PPS, we can just multiply by the ray weight and we're good to go, right? So I think that gives us the correct accumulated PPS, which then we can copy back in. In terms of this stuff here, where we're doing like lighting points with initial PPS and emission PPS, stuff like that, I think that's not really necessary anymore. So I think all that goes away. This goes away. That goes away. A lot of this stuff kind of just falls away because we've replaced it with something else now. So we'll be able to kind of butcher this up pretty darn good in a second here. But I think that's mostly the sketch. Like, that's basically what we're looking at. Let's go ahead and try to make sure that we can compile this down. So let's fix our like basic issues here. So I'm going to take this first sample point index. I'm going to change this to first light probe index because, again, remember, we're not going over the sample points anymore. Sample points will not exist shortly. The points that we sample at are now the actual light probes themselves. So we're just changing that name to reflect the fact that that's where we're sampling from. One past last light probe index, one past last light probe index. Here we go. This is... How many times is it going to take me to spell that right? There we go. This sample point dir index, that's off of the solution. I don't know why I typed a work there. That's wrong. Let's see what else we got. This is light probes, not light probe. Sample point index is light probe index now. Same thing here. So let's see where we're at. So get probe lighting for needs the spatial index, which we have, the solution, which we have, the probe sample P, which I think we have. Let me just make sure got all that right. But probably what we have to do is just predefine this, right? So yeah, I think what we want to do is just loft this up into here for now. Actually, so you know what we may want to do too? I don't know, but we may want to just make this in its own file. This voxel thing. Maybe, I don't know. Maybe that's just a waste of time. We'll see when we go a little further whether there actually is enough code here to make it worth splitting out. It might not be, but we need to be able to call those two functions, so I'm just going to pre-declare them there. So here we just gotta, this part is just a, in the transfer PPS, we want to be able to handle that ambient moonlight potentially as that comes in here. And so, oh, wait. I'm a dingus, aren't I? So, you know that thing I said about not needing the weights? Do we actually? No, I guess we don't, because we're always going to have an ambient light or black coming back for our samples if we don't hit something. So no, the ray weight is always correct. I'm not a dingus. But yeah, we do need to remember that there's a sample direction that goes with this, so we're going to have to figure out how we want to handle that in a second. But back here with our transfer PPS, where we do this operation, this part where we look at how much you're facing the moon, which is, I guess, what this would be about. This, again, is going to be the direction that we were going. And so that is actually this right here. You know what I just realized? Solving the emission direction this way is stupid, because that's always the ray direction. So actually, all you would have to do is just do this. Right? So that was stupid. Don't ask me why I did that, because it was dumb. So you don't actually need to do the subtraction there. There's no reason. You already know the answer. So all of this stuff is fine. And I think that's all good. So all we need to do here is say that emission direction is common in both cases. In here where we do use that emission direction, it looks like what we want to do is take the Z range of this guy, like that. Looks like that clamp was on the wrong thing, but that's okay. It would still work. It just was doing more work than it needed to. It looks like we just want to take that Z direction, clamp it, and multiply by the moon color. That tells us how much moon was coming in. It means the moonlight can't come in on an angle, which we may want to do. Because it would just take an extra dot product to do that, and that's a pretty cheap operation to do. So it seems like probably getting a direction for our ambient light would probably be smart. So I don't know. That seems like kind of just wasteful there. But let's take a look here. Yeah. So I think we're almost done. If we look at what's happening here, where we're distributing up our work here, we got the points per work and all that kind of nonsense happening, right? That's just going to be the light probe count now. So it's really just probes per work now. And we're slicing those up however we want. And this is just first light probe index. And this is probes per work. Right? One past last light probe index is going to be the same thing. And then in here, we're just looking to clamp this. So we want to say that if we were going to go over the end, I don't know that we actually have a light probe count in here, but we're going to need one, right? If we're going to go over the end, then we just clamp it off there. We also don't do any computation for light probe 0, apparently. And that's probably just so we can remember the fact that there is... If we are in a voxel that doesn't want to say there's a light probe there, then it can just be 0. But I think, actually... I guess what I might say about that is... I mean, I guess it's true that we don't need to compute anything for it, but it would actually be fine if that's a real light probe anyway. It doesn't matter. We can leave this in there. It's not a big deal. So I think now we're down to just the fact that when we're storing the accumulation, we don't really have a good idea of how we're storing the accumulation. So if we go back and look at the accumulated PPS here, which is somewhere, yeah, here it is. If we go back and look at the accumulated PPS, right, we're basically saying these two things don't want to be here anymore. This thing does want to be here anymore, but we don't want it to store just one light sample. We actually want it to store 6 light samples, and so we kind of need something that looks more like this, right? You know what I'm saying to you? And we could do it that way, but I don't really want to because I don't like these kinds of constructions. Is a pointer to 3v3s is just a little... eh. So what I'd rather do is just say, look, we're going to allocate this as if it had that stride in it. So, I'm sorry, 6v6. I think we want 6, not 3. I don't know why I typed 6 in there. So I think we want something more like that. Right, we want to accumulate the 6 samples, and I think they probably want to be contiguous. It's pretty hard to say. This gets into the part where I have never implemented a light probe system before, and had I implemented one before, I would probably have some opinions about how you want to store and manipulate these things. And the reason I say that is just because if you look at how this stuff is going to get gathered, it's unclear that you really want to gather it in ways that aren't sort of nicely done on a power of 2 boundary. I mean, maybe you do, but it would be nice if this thing was more power of 2-ish. And if you're talking about 6 light directions, then pretty much nothing you do, because there's a 3 in there, right? 3 times 2 is 6. So you're always going to have a times 3 in there. You're never going to get a power of 2. So you would much rather, talk about tracking, 8 light directions or something. I mean, I guess all I'm saying is you'd rather track 8 or 4 values. And so I don't know what the right answer is there. I think that's something we're just going to have to play with. So I think what I'll say at the immediate moment, is I'm just going to cheese this out, and then we're going to look at this in more detail because I feel like this is something important. And I just don't know what the answer is offhand. But I don't love this. Like, I don't want to be multiplying this by 6. That's just dumb. So that's just kind of garbage. I feel like you want this times 8. Just my 2 cents. So I think that's something that's going to require a little bit of squinkiness there, and we'll see. So on here, I'm just going to say, look, this is just going to be a 6 times this for now. We're going to nuke these guys. They're not going to happen. And then we'll take it from there. And this is not going to happen either, right? And we're going to get rid of that D eventually. So that's pretty much all I really wanted to do. That's the entire thing I wanted to do today, was just sketch out that routine and how that was going to work. And we probably should go in now and just start cleaning it up a little bit. We're not running it right now, so we don't have to look at what it actually looks like in practice or anything like that. But I think I've got about 30 minutes left, maybe, let's say. And so I think what I might want to do here is just, go ahead and finish up any cleanup that I might want to do. So just deleting stuff so that when we start debugging it, there's not just crap lying around that don't matter, right? So let's start by saying this stuff has to go. We don't care about these points anymore. Those are gone. The scratch arrays we got to take a look at, but those points are definitely gone. So this is gone, and what we would replace it with when we're dumping the data there is the light probe count. That's actually what we want to know. How many light probes are you pushing down into the system? And off you go. So in here, where we actually set this stuff up, the extended point count isn't a thing. We're not doing hierarchical sampling at this point, I don't think. So we're going to get rid of that as well. That should go away. The entropy frame count and t-update, all this stuff should accumulate these things. I think all that stuff is fine for now, although we may need to tweak it a little bit based on what we're doing. And we can sort of re-enable this stuff now too. Maybe that's what I'll do. But let's continue with just the sort of the trimming, if you will. So where we get this solution point count, and we get it from the group here, that sort of stuff. As far as pushing light probes on, I don't really know how I want that to work, but I think it should probably just be a free slot scheme, and people just pack and unpack out of here. So just to unpack what's going on in my head right now, we have the entity system, and it now operates on a caching basis. And we know exactly when entities come into and out of the working set, effectively. That means that it's pretty free. It's not 100% free, but it's pretty free for us to say that light probes just live in the lighting system, and they are allocated out to entities on an as-needed basis, right? And so when an entity comes into the working set, if it's a light probe, it just gets a slot in the light probe system, and when it gets removed, it just loses that slot, and that's kind of the end of it. The reason that I think that system makes a lot more sense than what we were doing before is there's a tremendous amount of unnecessary work going on right now where we're copying these lighting informations into and out of the system for no reason. We could do exactly the same thing with the light boxes as well, right? Meaning we don't really need to do what we're doing right now, where we are every frame pushing down all of the boxes that are involved. Because what we can do instead is just anytime something that is a reflector comes into the system, we put it into the lighting system, and anytime it goes out of the system, we take it out, and nobody needs to copy anything any other time, right? So treating the lighting system as another free list, effectively, which is just a thing that allocates out lighting resources to entities as they come in and out of the working set, seems to me to be a smarter way to do it than what we were doing before. I mean, correct me if I'm wrong, but that just seems like it saves a heck of a lot of work. That just seems like such a much better idea to me than what we were doing, which seems dumb. I'm not sure I want to start doing that right now, but I'm going to say, go ahead and say that's almost definitely what we want to do. Now, for light probes themselves, I could see an argument being made for just saying, look, the position of the light probes might change every frame. I mean, they can move around. Who knows what they're doing? We might not want to worry too much about that. So it's possible that the light probe positions and like the box positions, it's possible that those should themselves be recorded every frame, right? So if you look at the lighting box here, where you've got the radius and the reference color, the emission and the texture index and all this stuff, right? If all of this information that we're looking at here is updated every frame, then you'd want to rewrite it every frame because it wouldn't matter. But if a lot of that stays the same and it's just the P value that changes, that's, I guess, where the argument comes in. It's really hard to say, though. I don't know. That's a tough call. That's a tough call. What I will say is that light probes, this color value here should almost certainly be stored stably, and it should be stored probably outside in a table in the lighting system. And then when you allocate light probes, you allocate their indices off, and you write their P values in as part of the process. So I do think that light probes want to be stably assigned. Boxes, I'm just not sure. I just don't know. Yeah, I just don't know. So the other thing that I think we need to take into account here is we're not using the emission value right now. And we're probably going to need to. So the emission value, the way that we get lights into the system is having a non-zero emission value on a lighting box. And so maybe that's another thing I'll do right now before we forget. So if you look at the way our lighting hit works, right? Where's that value here? Here it is. So if you look at the way this works, you've got a ref color, and that's how stuff is reflected off the surface. But we also probably need here an emission value. And the reason we need an emission value is for actual lights. So reflection's one thing, but we need to actually be able to put things that emit light into the system. And so in this equation that we computed before for the lighting, here, where are you? There you are. Nope. There you are. So in this equation where we computed the lighting here, you can see that like this code doesn't allow you to ever get light into the system. The only light ever comes from the probes. Since probes themselves don't emit light, what do we do, right? So in order to emit light into the system, we do need an emission value to come back from our raycast results. And so when we take this, this transfer PPS here, in addition to the light that gets reflected, we also need to add the light that is emitted, right? So we would need here to take that emission value and multiply that by the sample ref color as an addition to the system, right? Hopefully that makes some sense. And if we wanted to, I guess you could do prior to the Hadamard, do the addition on the inside. No, because the fall off. Yeah, so I don't. Yeah. So I think you probably want to look roughly like that, right? And that's how your emissive lighting gets added in there. So that just means that the raycast here needs to remember this, which is annoying because it does add one more thing that needs to get remembered, but it's not the end of the world. It's a pretty cheap select, and that's it, right? So the hit emission here just looks like this. Okay, so that allows us to record that piece of information, which we definitely do want. Yeah, it's not a V3. How is it that? Yeah. So do we not have a way of getting components of F32s out? We must. So you can see us doing it here. I guess we were just meant to do this. I suppose. Not actually sure what we were supposed to do here. Oh, it's just the element. Okay. Not a great naming scheme there. Past me. So inside the point count thing here, we're back to where we were just looking at these basic changes we needed. For output lighting points, right? I mean, just looking at this stuff, this isn't how we're going to do this stuff anymore. We don't want to do any of it. We don't want to do any of this stuff. So I'm pretty sure we can just kind of nuke this code. It's not what we want at all. So I'm going to go ahead and do that. Because we're going to want to output our voxel and our light samples and that sort of stuff. Let me see what else we got here for errors. So I think I'm just going to leave it like that for now. I'm going to go ahead and go to Q&A because I think I don't want to start on anything else now. I want to kind of leave it till next time. because now we're effectively doing everything, and we just want to start doing the plumbing of moving those points in to the system, right? And going from there. All right. I may also pop over now. People wanted me to fix these problems. I added a very helpful comment here. So the problem is type names being reused as field names here. So I guess in handmade types.h, I'll just take a look at whether that's problem 286. I really don't like having to do this. I think this is an absolutely ridiculous thing. I would like to personally say that I think each and every person who approved this change to the C++ spec should never program ever again. Or if they do, they should not do it in a way that can ever affect anyone else's code. Because they just so very clearly have no idea what they're doing. I mean, there should be a path to redemption, I suppose. So if they can explain clearly and lucidly why this was an incredibly stupid idea that should never have been done, then they can program again. But until then, you're out. I thought I nuked that line. All right. So in the tokenizer, that was line 48 there. Now I get to change all of these. I really can't stress enough how anyone who makes a decision like this should never be allowed to design a language. It's nuts. It's like such a case of the inmates running the asylum, right? It's like, it is absolutely absurd. It is the kind of decision that is so incredibly bad that you just have to wonder why anyone would ever think it was a good idea. Maybe if you were like only programmed for a year or two or something, right? Because I'm sure I thought all kinds of stupid stuff when I was 9, right? But man, if you're at the point where you're actually deciding how a language works, this is not acceptable. Not acceptable at all. What's the other one? In-game editor. Somewhere in here. Align point edit. I guess I would classify this decision into the category of extreme arrogance, right? So if you're working on a language spec and you go, you know what, here's a piece of code that would work just fine. There's no reason the compiler can't generate 100% correct, unambiguous code for this. But you then go ahead and disallow it. All you're doing is saying, hi, I'm so arrogant that only the way that I think programs should be written is the way that they can be written at all in my language, right? And I have no idea how you get to that point where you're like, this would have worked, and we went out of our way to tell the compiler to not generate the working code because heaven forfend someone should do something in our language that we thought was just a little bit weird. Probably because we don't know how to program, and so we don't actually know what constitutes a good one. All right. No, it's not about undefined behavior. It's about diagnostic error messages. Undefined behavior is also completely unacceptable. There should never be anything in a spec that says the behavior is undefined. You should define the behavior using the appropriate bounds, right? Just say the compiler should generate the most logical, reasonable, least surprising thing that it can on this platform. That's all you need to say. Just don't say search and replace for undefined behavior and say the compiler is supposed to do its best to generate something like this for the platform that in question. That's all you need to say. And then everything works just fine. Never say it's undefined behavior because that is ridiculous. Why would you ever want to say that there's no constraints on the behavior of the thing? It's ridiculous. So no questions, it looks like, so I think we're good to go, right? Where's that little Twitch window I have? I always now try to check to see if there's anyone we can raid after we're done on Handmade Hero. And usually the answer is that nobody is available to raid of the people that I would raid. But it's always worth a quick little check, right? Oh boy. Where is the thing that you do with the raids? So is John live? No. Nobody's live. There's nobody to raid. So I guess we can't raid anyone today again. Again, no one to raid. Genos3 says, how do you know if you wrote undefined behavior code? Well, in C++, the answer is you did. It's basically impossible to write C++ code that does anything useful that doesn't have undefined behavior somewhere. So the answer is you did. The question is, how do you know where in your code you're using undefined behavior? That question is harder, right? Because there's so many places in the C++ spec where they just said it was undefined behavior that, I mean, I don't know how to tell you how to find it, right? That's why it's so bad. Compilers don't even warn you when there's undefined behavior, which is interesting, right? And that's part of the ridiculousness. I mean, like, for example, right? A typical way that you might see something like undefined behavior is, suppose you have something like, I don't know, the spec says if you overflow a signed integer, the result is undefined, right? And so the compiler can't really issue a warning because everywhere you ever operate on a signed integer, you might overflow it, right? So the undefined behavior only happens in the case where you actually do overflow the thing. So it would warn you about like every addition you ever add something to, you know? So it's pretty hard. But it just depends on, yeah, like which ones you're trying to find. It says there's a Clang UB sanitizer. Yeah, I mean, I don't know. I've never tried it. I don't know how well that works. It probably catches some. But the other problem too is that undefined behavior, usually there's a lot of things in C++ that actually you want to use the quote-unquote undefined behavior because it results in better actual CPU code for most compilers on most platforms. And so again, that's one of the really big problems with undefined behavior. It's dumb. There should never have been any... I mean, another way to say it would be, if you can't put bounds on the behavior of your program spec, you're not done yet. Your spec isn't complete if there's undefined behavior in it. It's not a spec. It's a goal, right? Undefined behavior should never appear in a specification. You should always have a clear statement about what the compiler is supposed to be trying to do in all cases. And if you have to leave room, meaning, hey, these different platforms, like for example, you know, maybe two different platforms have two different ways they handle certain floating point conditions. You don't want to specify things exactly because then you can't generate good code on both platforms. So you need to leave space sometimes, and that's great. But never, ever, 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 ever say undefined. That's absurd. Every single part of your spec can be defined. It can just be defined to accept a range of possible results. But define the friggin' range. Like, say what the space of acceptable results could be. Don't just say we don't know, because that's absurd, and you're not done yet. What's the weirdest macro? I don't know. I've never made macros that are that weird. I mean, the ones in Handmade Hero for the debug stuff are the weirdest kinds of macros I think I ever do. They're ones where you have to pass like the same argument like through 3 different macros to prevent the C stringizing and pasting operators from like stopping each other from working. You know what I'm talking about, right? Where we have to like generate debug names by passing like things through 3 times so that they don't use just the actual, like if you want like the underscore underscore line underscore underscore to become a string or something, you got to pass it through like full. What's the full screen purple flash that happens in your editor sometimes? Ask Alan. I don't know. It's just a bug in 4Coder. I don't know what the bug is. Have you seen the Grand Sealsless Air Explosion competition? I have. Someone sent it to me yesterday, in fact, on the stream. And it's pretty great. 2 of them work in C, like basically because they use includes. But I don't know that I really count those as much because includes are ambiguous anyway. So although it would be nice if the compiler printed out reasonable answers for those things, those aren't as bad. The C++ template ones are hilarious. Have you seen the Grand C++? Oh, sorry. Did you enjoy it? Yes, I did. Why is there no one to raid? John, Blow, where are you? Did you enjoy John's Macros vid? I was actually out at a movie, and I have not had a chance to watch it yet. As I didn't see it live. Pragmascript. Imagine a light probe that has no direct visibility to a red wall, but it could reach it via one indirect bounce. I don't think the light probe will ever get any red contribution from that wall, no matter how long you iterate, unless you cast secondary rays from surfaces. No. So that is definitely not true. Let me show you the diagram for that, just to make it clearer what's going on there. That is if I actually had a drawing program open. Okay. So let's just construct the case that exactly the case that you were talking about there, for clarity. So let's talk about secondary bounces here. All right, so let's draw the 2D case so it's easier for me to draw, but obviously it doesn't matter. It works the same in any number of dimensions because rays just go along their direction and bounce. So let's just construct a case where there isn't direct visibility in 2D, and then we'll go from there. So you say, imagine a light probe. So let's draw the probe. This is our probe. No direct visibility to a red wall. So in order to create no direct visibility, I'm going to have to do something like put an obstacle in here, right? So let's do, maybe our room is shaped like this. Right? And so if I want to, I can put a wall over here that I can't hit, right? This here could be my red wall. Make sense? Okay. So the argument is, what you're saying, is that this red wall can never contribute to the lighting of this probe, even though we might argue that it should. And the reason that we would think that it should, right, is because any light that hits this red wall could legitimately bounce off this wall, right? Let's say we've got a white wall here, or at least a gray wall. So it's a wall that doesn't change the lighting. So if we have a white wall or a gray wall up here, what we're saying is we know that if we were to simulate n bounces, we could bounce off of this wall here, right? And hit the light probe on an indirect bounce. So light comes from some light. We don't care where that is. I mean, we can put the light anywhere. It doesn't matter. But, you know, if there's a light here or something like this, right? Light hits the red wall. It bounces off the red wall, hits the white wall or gray wall, bounces off that, and then hits the probe. And your argument is our system won't ever pick this up. And I believe the reason you're saying that is because we only transmit light back like this, along this ray, right? Is that a fair statement of what you were arguing there? This is the transfer. Makes sense? Okay. So the question is that actually true? Meaning, is it the case that since we only transfer along this ray, we can never actually get this value back? And again, my argument is no, I would say that that's not the case. Now, there is one possible way this maybe could be the case, and that's if you don't put enough light probes in your system, right? And then that would be true. But that's going to be true of everything, meaning if you don't put enough light probes in the system, then your lighting is not going to be accurate, period, right? You need a dense enough sprinkling of light probes in the system in order to capture accurate lighting, period. So I don't really think that's a particularly good case to go down. So let's assume a reasonable set of light probes in this area, right? So I don't know how many light probes we would have necessarily, but you know, they're probably scattered throughout the environment, something at least like this, right? So each one of these points would be a light probe, and we probably have even more in 3D, right, because there'd be volume, but you've got light probes sprinkled around, right? Okay. So what actually happens in this system, remember, is every frame, each of these light probes will send out some number of rays. At the moment, the number is 18, but we can sort of tweak it for performance. So this number will typically be as many as we can afford, right? So this number is 18 right now. Maybe it'll only be 6, maybe it'll be 12. It's going to be set to the highest number that we can run and not slow down the game, right? So we don't know what this will be, but it will be something. And so each one of these light probes will send out that many per frame. What that means is on the same frame that this probe was sending out this particular ray here to hit this hit, it was also sending out several other ones, right, and hitting other places. But we all agree, because the construction of your argument presupposes it, we all agree that it will never hit this wall. Right? Because I specifically placed an obstacle that shadows that wall completely. So we know that it will only be grabbing from around here. So now the question is, can it ever actually receive light from the red wall? Well, remember, on the frame where this particular probe sent out all of those feelers, all of these probes also sent out their own set of 18 feelers, right? Or 6 or 12, however many. What that means is this probe, this probe, this probe, probably this probe, and maybe sometimes this probe, all hit the red wall, correct? Because this one probably sent something out in that direction every so often, maybe not every frame. This one very likely did. This one almost certainly did, because anything in that direction will hit it. Same with this one and this one. So we know that on any given frame, probably 3 probes at least hit the red wall. Right? So those 3 probes all picked up light from the red wall on that frame. Make sense? And which probes were they? Well, they were these 2 probes, which probably don't matter in our case, and these 3 probes, which definitely do, right? This one occasionally, this one fairly frequently, this one almost always. When this light probe hits anywhere on this wall, it will definitely then sample lighting from probes which have hit the red wall on the previous frame, right? It will then gather that light from those probes, which includes the contribution from the red wall, leading this probe to now have some red wall contribution. Make sense? So the answer is, in one frame, can you get light from the red wall? No. In 2 frames, can you? Yes. Now, in our system, we average over at least 60 frames, I think. So, as long as that number doesn't drop to 2, which would be ridiculous. I mean, we may drop it down to something more like 10 in the future if our lighting is really good. But we average over at least 10 frames, and we always use the lighting from the previous frame. So for secondary bounces like this is sufficient. But the answer is the number of frames you average over is how many secondary bounces you get. So actually, over 60 frames, we're actually doing what amounts to 60 bounce lighting. Now that 60th bounce is a fraction of a contribution, right? It's not happening very often. So it's kind of meaningless to say that. But certainly within those first few frames, 3 frames, 4 frames, 5 frames, we're definitely taking into account all those bounces at a relatively high shading rate, right? Was that convincing? Or not? Okay, awesome. Sounds like that was convincing. And yeah, and again, this is by design. When you're doing real-time lighting, you don't usually have the kind of computational power necessary to do multi-bounce diffuse lighting inside one frame, right? It would be nice if you did, but you typically don't. And so what you try to do is specular, like highly reflective surfaces. Those don't require spreading of bounces, right? So what I would say is specular lighting you try to do within one frame because delayed reflections wouldn't look very good. So you try to do specular inside one frame. Diffuse lighting where things are scattered a lot, you never try to do those all in one frame. So typically what you want to do is design a solution that allows you to propagate that light over several frames. And because diffuse lighting is exactly that, it's diffuse. It's hard to see specific changes. They're gradual anyway, so it tends to not be very objectionable in terms of artifacts because diffuse lighting can't change that rapidly anyway, right? So the worst case for you really is when you're doing that kind of frame-by-frame propagation is if you turn off a light, then the propagation of that light, it will kind of fade out rather than instantly going out. That's about the worst case for diffuse lighting that you're going to see, and that does not bother me in the least, right? But also, I mean, I should say, separate than that, that's also one good reason why the faster you make your lighting, the better, because averaging over, 60 frames or something, it does mean that you can't do like flashing light propagation very well or things like that. As you get that number down, if you can get it down to 8 frames, 16 frames, then a flashing light sort of does work a little bit. It can't flash too fast, but it could flash like once a second and still look okay. But so you do want to kind of, it's still worth your while to try and get it down as low as you can. And so denoising and getting yourself down to a situation where you can do 8 frames of blend, 16 frames of blend, something like that, not 60 frames of blend, 120 frames of blend. It does help you. It does make the game better and more interesting to look at to get that speed down. But again, that's really all you're up against for these sort of longer bounce sort of things, is just trying to get it down for like, so that lighting changes as lights move or turn on and off. You're just trying to get some of the lag out of it. You all done with questions? And yeah, for the folks on the chat that are talking about signed overflows, so again, like undefined behavior, there's never an excuse for it, in my opinion, ever. But this is why I was saying non-specific behavior is still okay. And the reason for that is because you do need the compiler to have flexibility sometimes to generate good code. And so what you want to do is you want to define the range of possible answers to be the range that is necessary for good optimization, but you don't want it broader than that, right? So if you don't want to specifically say what happens when a signed number overflows because it may cause problems for optimizing compilers, that's okay. What's not okay is just saying it's undefined. That's totally not okay. Because at that point, all programs are basically broken. All of them that ever add two signed numbers together, right? Because who knows, right? I mean, you may have needed to check for those things, do if statements, or you wanted to know what was going to happen. You can't just say it's undefined everywhere. Say what you need to say and nothing more, right? If you need to leave ability for that, go right ahead. And furthermore, just add a keyword. If the person wants to know that a signed overflow will wrap, let them specify that, right? Let them put a thing in there that says this signed type of signed integer has to wrap, Mr. Compiler, right? Just do it that way. There's no excuse for undefined behavior, never. I've never seen one, and I don't think I ever will. You can always do a better job than that and still get all of the same benefits. It's just lazy and it's wrong. It shouldn't occur in a spec, ever. There should never be something called undefined behavior, ever, for any reason. You can define boundaries, do that, or you can add control to the programmer, do that. But never, ever, ever just say something's undefined. It's just unacceptable. All right, looks like we're done. Looks like we're done with questions. There was some other. Yeah, it's this. We got to go fix this one too at some point. That was the other Linux compilation bug there. All right. Thank you, everyone, for joining me for the episode of Handmade here. It's been a pleasure coding with you, as always. We'll be back next weekend to start actually pushing light through the light system now that we've sketched out all the code. It's just bookkeeping now, but we want to get that bookkeeping correct. So we'll start on the bookkeeping, and that's when we'll be able to start debugging and testing it and getting to the point where we think it's actually propagating light correctly, and that'll be fun. Once we get that done, I think maybe next weekend we got a shot at getting that stuff all working. We may not, depends how many bugs we run into. If we get all that stuff working next weekend, that would be great, because then we're just down to push into the GPU for our lighting stuff, and that's going to be pretty cool, right? In 2 weeks, if the schedule posts on Twitter. Did I not schedule anything for? Wait, is the schedule busted? Oh, weird. It looks like I forgot 2 days. The 24th and 25th. Hold, please. Is that intentional? Am I gone that weekend or something? Am I on vacation and just don't know? Nope. So that was 100% unintentional. The 24th at least should have been scheduled. The 25th, maybe not. Um All right. Hold, please, everyone, while we real-time edit the schedule for Handmade Hero. I should update that because I think that's wrong. So I don't know why I skipped that. I think I was just putting in a bunch of dates and just forgot, I guess. 2019, 08. So it should be, what, the 24th? So maybe what we'll do, because I guess I made a mistake there, maybe next weekend what we can do is on the 24th, because I do have something kind of scheduled on the 25th a little bit inconveniently there. If I'm looking at it, so I'm not sure how I want to do that exactly. But what I might say is let's just say the 25th is off, but the 24th is not. I'll also note this in the schedule. Does that look better now? Let's take a look. Schedule bot, what do you say? There we go. All right. So in that case, since we will probably only have one stream that weekend, we'll have to decide. Maybe that would be a good time to do the to explain how mesh skinning works. Maybe, since we'll only do one that weekend, so maybe we'll do a Handmade chat. Maybe we won't. I don't know. We'll see. But then we'll resume at any rate on August 31st, September 1st at least. Then we will resume doing the lighting plumbing if we don't do it next weekend. All right. Anyway, regardless, I hope to see you back here next Saturday for whatever we end up doing on Handmade Hero. Until then, please have fun programming. I'll see you on the internet. And as always, if you want to follow along with the source code at home, you can always pre-order the game on handmadehero.org, and it comes with the source code if you want to play around with it until we next meet. That's it for today. I will see everyone back here next week. Take it easy, everybody.